and earthquakes. I could ask a different question rather than earthquakes. I could ask, is there a connection between fracking and the quality of aquifers in the region? Muted. It's always because the mic is muted. Okay. Hi, everyone. Welcome to Physics University, or at least another day in Physics University. Okay, so I'm Brenden. We'll be doing some fancy, weird. I guess it's weird. It's fancy. It's very weird. I'm actually going to be presenting or talking about the kind of the foundational principle of the research that I've been doing. I guess I find it interesting. Not everyone may find it interesting, but I certainly do. And so what we're going to be talking about today, if I, what direction do I want to judge this in? Let's zoom myself down a little bit, pop myself up into the corner, fly around just a little bit, maybe go a little bit smaller. Now I'm realizing I'm not going to be able to see the title, but I want to be able to write, so maybe we'll go into the bottom right. Bounce around all over the place. Okay. So what we're going to be talking about today is causality. Where to even begin with such a broad and kind of nightmarish subject. So fundamentally, what is causing me to want to talk about this? What is causing me? Why do I want to talk about this? Do I give the real answer or like the PR answer? The PR answer is I'm very fascinated by my research. Not yet. Yeah. Okay. Okay. Now that it's recording, we're just gonna awkwardly restart that because YouTube wants me to do what I'm doing. Okay. Hi everyone. Welcome to Physics University. This is Brenden, and today I'm gonna be talking about causality. Maggie asked a question in chat. What is causing me to want to talk about this? I think it's a bit. I'm pretty sure it's a bit, but I'm gonna address that question seriously anyway because it is a nice question. One of the reasons that I want to talk about this is that this is very, very relevant to my research. I managed to cheat the system a little bit and go from a research project that was explicitly about biophysics to a research project that was more closely related to causation, because I'm interested in the fundamental question about causality, which I guess makes me like a philosophical hack or something like that, which is fine. So I think the other reason, other than just my research, is that causation is, I think, one of the most important questions that we can answer as a scientific community, which is to say, all of the policy that comes out of science should be based on causative statements, right? Like, if I want to make a position claim, if I want to modify the way that we conduct ourselves in society, I should have an evidence-based, if-then kind of procedural argument that I'm making about the policy that we're talking about. And hopefully, the way that I'm arguing that is that if we do A, then society gets better. You could also imagine different scenarios of that kind of causative argument, such as if we do A, then our company makes more money, or if we do A, our product is cheaper, or less cynical ones, like if we do A, then our product is better for people. Yeah, it's definitely not usually those first two. And so one example that I will give of this, where it's actually really, really important right now in the modern day, actually, we already have the science on this, we already know, but I'm going to talk about it as if we don't know the answer to this question. I want to know, oh, my tablet is not level. Oh God, that's a mistake. I got it. Okay. I want to know, say, for the sake of argument, pulling this out of nowhere, is there a connection between fracking and earthquakes? I could ask a different question rather than earthquakes. I could ask, is there a connection between fracking and the quality of aquifers in the region? Is there a connection between fracking and, say, yeah, that's a pretty cool question mark. I'm pretty happy with that question mark. This symbol in the middle here is I'm trying to denote that there could be 2 arrows, there could be 1 arrow, there could be 0 arrows, and so I put a question mark over it, a little Riddler question mark. Because in principle, as a scientist, when I approach this question, I don't know. Actually, I forgot to say something. Thank you, Lying Magpie, for the follow. I saw that in the feed before I started stream, and I blazed right on past it, so sorry about that. Thank you for following. If you're ever around here in chat, feel free to ask, or anyone, feel free to ask questions about what we're talking about, because I know that we're physicists, and the perception of us is that we never, ever, ever stop talking and just love to hear ourselves talk. But it's not the best thing in the world to just sit here and lecture into the void. So if anyone's hanging out and wants to ask questions about anything I'm talking about, or anything in general, like, please do so. Yeah. Okay. So as a scientist, when I look at this question and I approach this question, I say, well, I don't know. I don't know if there is a causal relationship between these two things. Again, causal could mean either directionality to this. Clearly, I'm using this as a introductory case for a very specific reason, but these arrows could in principle go in either direction, or both could be true. Now, it would be pretty goofy to imagine the leftward arrow implying that earthquakes cause fracking. I feel like that arrow doesn't happen. I feel like I can reasonably conclude as a scientist that I don't need to worry about that arrow. So I'm going to maybe redefine my question rather than this one to be, does fracking cause earthquakes? Because I feel like that's a much more accurate question that I'm trying to answer. So as a scientist, the way that you approach a situation like this is you say, all right, well, what I'm going to do is I'm going to sit down with a community of my cohorts, or people who are even more knowledgeable than I in the field. And then what I'm going to do is I'm going to compile some amount of data. Usually when we're talking about causality, we usually mean causality in a particular order in time. And so we usually mean things like if A, then B. So the way we think about this is, if we do A, does B happen? That has a couple, and there's an even weirder question mark. So this has a couple like important ramifications. And I will say, just for the sake of referencing, a lot of the things that I'm going to be, or all of the images that I'm going to be showing, and some of the kind of foundational bits of one method to investigate causality that I am very, very familiar with. I'm going to be referencing this Causality in Complex Ecosystems paper. It is on Science Magazine. It is not publicly available. They have not uploaded an archive of the paper, so it is not very pleasant to go and track this paper down. You will need some kind of university-sanctioned account to be able to view it. So this paper is sort of the seminal work of the most important bit of causation advancement, other than another method which we are not going to talk about today, called Granger causality. This paper out of the Scripps Institute from the Sugihara lab is one of my favorite papers that I've ever read. It is just the paper to me about causality. And so I'm going to be pulling some of their figures just for the sake of presentation, because their figures are wonderful and the paper itself is wonderful. If you do have access to it, I would highly recommend reading it. So the way that you approach a causation problem, just to like summarize what we've been talking about so far, is that we want to collect a series of data. So what goes in this if we do A is time series data. Now, by time series data, I mean I'm going to think about some number of quantities that I want to measure. I'm going to think about the interval over which I want to measure them. And then I'm going to measure some other amount of time series data and see through some mathematics and I don't want to say that yet. So I'm going to take time series data for the two things that I'm interested in. And then I want to somehow look at the functional form of the data, look at the shape of the data, look at various weird mathematical constructions of the data, and see if I can establish anything about the most important word in the sentence, which is, why are you doing that, OneNote? Which is the word does. The does here is it is implicitly a question, right? And this is where the hard stuff is. This is where the difficulty is. The does part, it's really easy to take time series data about fracking. You can just go in and look at how often it happens and where it happens. It's pretty easy to take data about earthquakes. We're taking it all the time, right? The harder question is, how do we show that there is a causative effect of A to B? And that's what I'm going to spend the bulk of my time in the stream today talking about. So let's come up, I don't want to get to that yet. Let's come up with a slightly simpler model. I'll stick with the purple. So what I'm going to do is I want to imagine a system that we are all, as physicists, incredibly familiar with. I think of everything in the world as the system. This is two masses connected by an ideal spring. So here's a mass 1, here's a mass 2, here's a spring constant, here's a spring with constant K. I don't really care what it is. It's not really relevant what's happening with the spring. Or any of the physical properties. I don't care about the mass. None of this matters. This is just a model that I'm going to use. So this system, these masses are obviously connected. They are attached to one another. And so there is this a priori, which means before we do any investigation, we have prior knowledge that these two things are causatively connected to one another. They are attached by a spring. If I jiggle mass 1, the spring will compress and relax, and mass 2 will move. And like, that's just, I feel like that's kind of natural. If you haven't ever seen spring masses before, I'm sure, I think Austin's done at least one problem in our history of problem solving here on the channel that has talked a little bit about springs. I might be completely fabricating nonsense there, but I believe we've talked about springs a little bit on this channel. So if you want to learn more about how springs work, this is not the video for that. So what I want to think about doing is I'm going to push mass 1. And I want to look at the displacement of mass 1 from its, let's do this in orange. I want to look at the displacement of mass 1 from its equilibrium and the displacement of mass 2 from its equilibrium. These two things are just resting there. They're not going to do anything. And I'm just going to assume that they're not going to I'm not going to like worry about them translating or anything. Like, they're attached to something somehow. Maybe the spring is pinned at the middle. I don't care. Like, the important thing is that I'm going to jiggle 1 and stuff's going to happen. Let me make this pen a little bit smaller. So let's say that I track the position of mass 1 as a function of time. So this might be, let's do x1 as a function of time. And let's say I give it a push. And that push, just for the sake of argument, let's make it a little curvy. I don't really care. I'm going to push it at some initial time t0. And I'm just going to make it push like that. And it's going to be this little bell shape. Okay. As I compress mass 1, mass 1 has deviated from its equilibrium, therefore the spring has compressed, therefore the spring is pissed off and doesn't want to be where it is. And so the spring is going to push mass 2 away and propagate some of that disturbance to mass 2. I don't necessarily know if mass 2 will move the exact same amount that mass 1 will. But I do know something very important about this from a physical perspective, and that's that mass 2 is not going to move instantaneously. There's a couple different ways to think about that. You can think about that there needs to be some amount of time that the spring compresses by, because these things are forces, and forces need to act on objects for certain amounts of time for them to move. So obviously there's a finite amount of time that this propagation is moving down the spring. If you're interested in that idea, I think we've also talked about waves here a little bit on the channel, so that's kind of cool. So you can think of this as a wave behavior. You're watching a disturbance move down a medium. But what's important here is that this thing is not going to happen at T0. It's going to happen at some time later at T1. Now, how much later that happens depends on a lot of things. It depends on the stiffness of the spring. But you can imagine through some of the features that we talked about with Maggie, with her last talk on the channel, it takes time for the information of your push to travel down the spring. So from a relativistic perspective, it also makes sense that this is not an instantaneous thing. So X2 may not have exactly the same shape. It will probably look pretty similar. X2 will probably not be the same total displacement. It will probably not displace quite as much. But it's still going to do something kind of similar. So this happened at T1, which was some time later. And so what I could do is if I was being like really, really, really primitive, like I want to do the most primitive analysis of how these things are causatively connected to one another. Now, again, I already know that they're causatively connected. So to some of you, this is kind of circular. But I just want to demonstrate one of the primitive methods of causation, which is the first one that we're going to talk about, which is the correlation. My camera is covering that up. So right now what we're hinting at is the idea of a correlation. And a lot of you, particularly those of you that grew up right around the same time I did, I binged the hell out of Mythbusters when I was growing up. Because I was a little science boy and I just wanted to watch Mythbusters all the time. And I think probably the most resounding bit of information I got from that show was continual statements of correlation does not equal causation. And as a science community, we have moved very far beyond the idea of correlations being the end all be all of our analysis about causation in the system. So we don't do this anymore. We have much better method. Well, depending. Some cases we do still have to do this because there's, I won't get into that. But what I want to think about doing is I'm going to grab this. I didn't quite grab what I wanted. Do I have to surround like the majority of the body? There we go. I'm going to grab this function. Here's my little curve. This is my curve that represented my displacement. And I'm just going to look at it. And I'm going to say, wow, those two things look pretty similar to me, except this one was shifted a little bit in time. Now I say to myself, when I see two variables that look like that, where they have basically the same shape, they're shifted a little bit in time with respect to one another, and I have evidence to think, or I have a presupposition or some amount of intuition that there may be a causative connection to these things, well, then I say, well, variable 1 got big, and then variable 2 got big. It looks like variable 1 made variable 2 get big. And I mean, literally, that is what correlation, that is what that is the statement of two things being correlated, is that their functional shapes look the same. And I know I have this little function down here. Let's ignore that. We're not getting to that point yet. That image, in fact, I can probably bet, will OneNote freak out if I grab it from here? Yeah, it's not. That's fine. Let's ignore the equation at the bottom of the screen. That's like behind the curtain. Mathematically, I'm gonna write something a little scary for a second, so I'm sorry. Mathematically, you would consider the correlation coefficient to be where we're going to integrate out, frankly, as far as we need to. This may look weird to you if you are unfamiliar with physics. This is an integral, and if you've taken calculus before, you're pretty familiar with what an integral is. What we're doing here is we're taking the product of two functions and adding them up. If these two functions are what we call in physics normalized, which means, under some condition, they have something that we could associate with being unit length, okay? So whatever I mean by normalized, usually for a vector, I mean it has length 1. These are functions, so what length 1 means in this situation is very complicated. But let's just assume that f and g are nice functions in the way that I mean by nice in physics. what's going to happen here is that if these are the same function, this is going to give me, so if the same, this equals 1. And if they are different enough, totally different, then this is going to give me 0. This can also give me -1 if the two functions are negative with respect to one another, right? And if you're paying attention to the physics, you can see by my statement of normalized means that if I take f of t times the f of t and integrate it, I get 1. That is my statement about being normalized. But this gives me a really nice mathematical way to think about what's happening with my causation, right? I said if two things look similar, they're probably related. And that, I think, is the most like primitive human emotion for causality you can possibly have, right? Like, this is a very gruesome example, but it's the first thing that came to my head. Like, I just burned my hand. That sucks. There's a flesh-shaped imprint on my stovetop burner. I might think, because those shapes are the same, that there was some connection between those two events. And literally, in the mathematics, that's what we're doing with time series function, is we are very literally identifying the shapes of these things and trying to establish a connection between shape and causation. And if you're perceptive, you can kind of already tell that this is going to be a problem, because limiting your scope of what things can be causally connected to things that look the same is very limited, to say the least. There can be things that look different that are actually very closely related to one another and very, functionally dependent on one another. You could imagine that the density of fog in a region and the temperature of the air aren't going to be the same plot. They're not going to look the same like these functions do. They're going to be different. They'll have different levels of fluctuations. They'll have different time series at which you measure those things, right? They'll have different scales, different units. But obviously, the temperature affects the density of the air. Like, yes, that is what happens, right? So there is a causal connect between those two things, and we know that there's a causal connection because we have physical models that tell us that they're connected. And those models are very highly predictive, they give us good results, and so we keep them and say they're real science. What we need these causality tools for are things that we don't have models for. This spring mass example, really bad. We know they're causally connected. We can literally look at them, right? We want to use this to investigate things that we don't have models for. We want to investigate, if you think about the set of things that you can write a physics model for, and literally everything else that you can't write a direct model for, this thing over here is infinitely bigger than this thing is. We have very few things that we can successfully model in physics. Most of the time, the things we learn about physical systems come from not new insights and new models, but taking models we're already familiar with and we already understand and applying them in a new context. We have very few tools in physics to analyze the universe around us. And so we are desperately in need of what we call model-free solutions or model-free methods, where we don't need to say anything about the underlying physics interaction to conclude anything about the system. We simply need to build an algorithm, shove the data into the algorithm, and just worship the numbers that come out. Okay, I'm being a little critical of modern neuroscience right now, because that's what they do. But whatever gets you grant money. So we're going to move on a little bit, and I'm going to show you a plot down beneath. Like all the other pretty figures, this is coming from that Sugihara paper that I linked about, or I dropped the DOI at the top of the thing. If you're unfamiliar with DOI links, you can type this in to Google, just the number 10.1126/science. Whatever, and the paper will just pull up. So DOIs are pretty cool links. They're it's like a book number thing. The ISBNs that you would have at the library, it's just a universal indexing method that just is a truncated form of finding papers. So if you know the DOI for a paper, you can go and view it pretty easily. So we've talked about the spring mass example, and if I had a methodology of correlations to like which I have down here to analyze this system, I could pretty easily conclude that 1 and 2 are causatively connected because they are similar looking functions. I might also want to say something about where they happened in time. And so I can come up with, I'm going to pull the axis along with me. Yep, I am. I can come up with methods of adaptations of this correlation method, where I think about checking not just if the functions look similar, but if the functions look even more similar if I slid them past one another. Which is to say, these two peaks do not happen at the same time, right? Function 1 starts at t0, the next function starts at t1, which is later. And so if I put these directly on top of one another at the times they really happen at, I get something that looks like this. I don't know, those two functions look pretty similar to me, but they're happening at wildly different times. And so if I actually take this integral, I'm not going to necessarily get something that gives me this 1 or 0 property that I have down here. What I could do instead is think about sliding these functions past one another to try and find a point where they have a maximum correlation, and then figuring out how much I had to slide them past one another and thinking of that as the delay in time that these events happened. Okay. Ultimately, all the rest of our analysis today and all causality analysis in general is looking at two functions and trying to figure out which one caused the other. And the black box that happens in between is radically different depending on the context that you're investigating. Some things correlations are very appropriate for. I'm about to show you a plot where correlations are very obviously not a good tool to use. So let's look at a bad correlation system. So this plot right here, which I'm going to zoom in on just a little bit. This plot comes from something called the Lorentz attractor, or the Lorentz system. So the Lorentz system, and in fact, its differential equation is down here, and I'll show you a little bit more about it in a second. So these are three, an x and a y and a z term, coupled differential equations. So if you're unfamiliar with differential equations, this is meaningless, and that's okay. It should be meaningless because differential equations are a bunch of nonsense. If you are a little bit familiar with differential equations, this looks very complicated, and it's not very well, it is separable, I think. I haven't actually tried to solve this before, and I have no intention to. I think it's separable. It's not pretty. If you're curious about the physical background of these equations, the Lorentz system arose first in terms of when this model was developed. It was first applied to weather systems. So this describes a 2D plane of, air, but really a temperature-dependent medium that is being heated from below and cooled from above. And if you say, hey, that sounds like all of our atmosphere all the time, you'd be right, which is why this is an incredibly well-studied model. It also shows up in things like lasers. It shows up in osmosis. It shows up all over the place. This is a very, very common model that we use in a lot of different places. You typically don't see this even in graduate school in physics because it's just kind of intractable and gross. This is also one of the simplest examples, other than something like a double real pendulum, where you get chaotic regimes. So if you're unfamiliar with that language, all of what we do in physics, if you took an introductory physics sequence in college, or if you took physics in high school, you dealt always with deterministic physics, which is to say, I see a system, I write down the equations for that system, and I can figure out what it does at a later time. Chaotic systems are not deterministic, which means that you can't actually predict the future motion, because what they do is not as simple as, what it's been doing. They have a lot of very complicated dependence on where the system currently is and where it has been. So chaotic systems are very, very, very difficult to analyze, and so we basically never talk about them until you desperately need to, if you're like an atmospheric scientist. So these two blue and red curves here are the x and y coordinates of this Lorentz attractor In a chaotic regime, so the Lorentz system is chaotic in some choices of parameters, choices of sigma and rho and beta. Some of them leave you in deterministic regimes, some of them leave you in chaotic regimes, and so this plot comes from the chaotic ones. So at some points in time, x and y look perfectly correlated with one another. That's this, I got an error from OBS. An error told me it can't record. Your computer run out of space? I guess I don't want to do that right now. It might have, because we have a bunch of VODs. That's fine. I'm not worried about it. We can always pull and upload whole VOD, and I don't care. It's not a problem. So, in this first regime, these two functions are highly correlated. They look literally identical to me. You can barely even see the red curve in the first region. In the second region, these two functions are looking very anti-correlated with one another, where that means that their functions are upside down with respect to one another. So where the blue has a peak, the red has a trough. Where the red has a peak, the blue has a trough. So this region would give me, a correlation coefficient by this model I gave up here. This would give me C around 1, this would give me C around -1, and this would give me C around 0 over the whole region. Because for some of the region, this is going to be an in-between state. So this is going to be somewhere like around half. For some of it, there's no correlation between the two of them. There's no functional overlap. They're totally flat with respect to one another. And then they behave really nicely for a little bit, and then they kind of get out of sync again. So you can see that you can already see a very important message of today taking shape, which is when you see data presented to you that includes an argument about something. For example, fracking causes earthquakes. You have to be very, very cognizant of what regions in which that data is being presented. Some here, if I showed you blue is fracking and red is earthquakes, you would go, oh my God, we need to stop that right now. Although we do have data that looks like that and we haven't stopped yet. So, or if I showed you B, you might say, well, those two things, I don't know, maybe. Or especially if I showed you C, particularly this first bit of C, you would throw me out of the room and tell me I was a terrible scientist. And this is a problem with data. You always need to be asking the question, where does the data come from? What regime am I looking in? What models went into discussing this data? What assumptions did we make about the data? Like, I will tell you, no one in chat, I will tell you right now that there is no data that exists agnostic to biases and motivations, right? There is no set of data that I can take that is unmotivated. Everything we do is motivated by something. In the political science world, we call this lack of divorce between what we are investigating and what we are, and like our fundamental presuppositions about the universe. We call this a statement about propaganda. I obviously will get thrown out of the science world if I call science propaganda, but you can easily propagandize science. My background is as a data scientist, and you can hand me any set of data and I can make it do anything you want. I can change the resolution. I can change, by changing sampling rates. I can rescale things. I can look for regions where it shows what you want me to show. And if you pay me enough money, I'll do it, right? Because I'm in a society where I need money to survive. And so when I look at systems like this and I see this question, does fracking cause earthquakes? Like, again, we know the answer to that question. But like, who's asking the question and why? The foundational principles to how you observed the data and how you took the data and why you took the data are inseparable from the data you took. And so that's a little bit of a segue about not trusting data that you see and being very critical about the data you do look at. Even if you are not an expert, you could still ask the right questions to detect, hey, maybe your data wasn't as honestly represented as it could be. I am reminded of studies about the connection between vaccines and autism. This is a classic question, right? Like, this is probably, like, the anti-vax movement is large because of one scientist who had a financial stake in proving that there was a connection between those things. And even though that person lost all of their credentials, their paper was redacted, and they were laughed out of the medical world, they still peddle their science, and people still uncritically digest it. The number one thing to leave, the number one thing that anyone watching this VOD or in stream needs to understand about data, like the number one theme from today's discussion, is that, and I'm going to hint at it, it's not what I'm going to be teaching you necessarily, but be critical of the data you look at and be critical of the information you read, because there are people out there whose entire careers are built up around manipulating numbers to make certain stories true. And they are far more common than you think. Let's put it that way. Okay. So, did I leave a little bit of space before I got to... Yeah, I left a little bit of space. So, maybe what I'll do is I'll just move this image over. I'm going to build up some science really quick. Or a little bit. This set of stuff over here. I can imagine that there is, for some choice of sigma, rho, and beta, that there is some solution. Some functions, x of t, y of t, and z of t, that together solve this system of equations for all time. There might be several different choices of several different sets of x of t's, y of t's, and z of t's that solve this system. And so what I can think about doing, let's just take x for a second. What I can think about doing is I can think about, well, I could plot x versus t, and I could plot all of the different functions of x versus t for all of the different initial conditions that satisfy a given set of these parameters, sigma, rho, and beta. And I could say, all right, I've got one that's maybe going to look like this, and I've got another one that'll look like this, and I've got another one that'll look like that, and then maybe I got a little one in here, maybe I got a big one over here, and this gets really tedious really quickly. This is a terrible way to visualize the solutions to some set of differential equations. I don't want to do this. This is garbage. What I'm going to do instead is, rather than, yep, hey, look at that. You ran out of space on your hard drive. Isn't that fun? You ran out of so much space that OneNote crashed. What? I mean, let me do this real quick. No, it's fine. I'm just gonna like delete something in the background while I'm sitting here. Because I know for a fact that we have videos. Like these things. Some of these, right, are nonsense. We don't know. We don't know. We wouldn't know because, God, these are 12 gigs. Fine. We're just going to hope that OneNote isn't going to do that. If it does it again, I'm not going to go deleting VODs on stream. So if I get another error and OneNote crashes, I'm probably just going to end early. Because I don't want to deal with it and it's stressing me out. So it's fine. It's fine. It's not, we're fine. We're fine. We're fine for now. So what I'm going to do instead is, rather than plot x and t, right? Let me rehearse or go back over what I was just talking about. So we had those set of squiggly lines, and plotting x, all of the different x's versus t of all of the different things that solve your system of equations is a truly awful way of visualizing the set of solutions. It doesn't tell you very much. It's very opaque to analysis. So what we will instead do is something that many of you are going to be very uncomfortable with, but I'm going to draw x. I'm going to put my x stuff on the x-axis, and I'm going to put x dot up here on the y-axis. If you're unfamiliar with this notation, X dot is a time derivative, so this is dx dt. This now is a plot of position versus velocity, or something like that. This set of equations over here, the x, y, and z coordinates are, I think, referring to the temperature at a position in the, or how the temperature gradients change in x, y, and z. I'm not 100% sure. Going back to my spring mass example, this x versus x dot makes a lot of sense, right? I'm plotting the position of the object versus its velocity. If I put a point here, that point means at some time, my object had x naught position and my object had v naught velocity. That's a point in this diagram. That means at some point that the system, some point in time, it doesn't have to be, nothing in here, there's no information about the time that happened at on this plot. But this was observed in the system. I can, of course, take data about the position as a function of time, and that will tell me the velocity is a function of time if I take finite differences or a derivative. And so this point, its existence implies that at some point the system was at position x with velocity v. At some point at some other time, the position may have been at, the system may have been at another position and another velocity. And I can think about dotting all of the particular position, all of the particular states. That's what we call each of these points, is it's a state in the system. I can think about what this system looks like if I just sample a bunch of states and let it run. And what I might find is that the states fall on kind of a curvy thing. And maybe what the system is doing is it's just kind of like proceeding around this little spiral curve. And so it's going from low positions with low velocities to high positions with high velocities and back again. Maybe if I keep going and I fill in the density of this a little bit more, maybe I find that these are actually like continuous states and I just wasn't sampling quick enough. Maybe it looks like this. Maybe it's not just a single one-dimensional curve. Maybe it's a volume. Maybe all the stuff in here are solutions to this differential equation for, again, a particular source of sigma, rho, and beta. This is what we call an attractor. And what we've drawn here is state space. This is not the xy plane. This is a different kind of vector space that I'm living in. This is a different kind of coordinate space that I'm tracking here. We call it state space because it's a space in which you can represent states. Yay. And this attractor represents the set of solutions to my differential equation. Now, what I can do with this attractor, which is pretty neat, or I think it's neat, maybe I'm just broken, is that if I pick a point in the attractor, I will stay inside of it forever. And so maybe I pick this point and I'm just gonna like loop around and do funky things inside this volume. I'm not gonna leave the volume. That's why it's called an attractor. It doesn't let you leave once you're inside of it. This thing represents all of the information we can know about our differential equation, because all of its solutions are contained within this shape. Funny shape. Funny circle shape. So now, if I was to think about, I've kind of already made this statement, but I'm going to make a bold causal claim to everyone that every, or maybe, is this a theorem? Is this a lemma? What do I want to say? I want to say every observable, I'm gonna define it and then I'm gonna talk about what it means. Every observable quantity is a projection of a holistic attractor. This is somewhat imprecise language. So every observable quantity is a projection of a holistic attractor. What that means is that there is a differential equation that represents the universe. And every point of data, every quantity that we could possibly want to measure is some subspace of that gigantic universe's differential equation solution. Okay? This is a philosophical statement about causality in some sense. It is a mathematical statement, but it is much more philosophical than it is mathematical. It says that all things are connected. And they're so connected that causes are not readily separable from their effects. This is quite literally a huge departure from traditional notions of causality. Correlations and the ever popular method that I'm not talking about today, Granger causality, assume that causes and effects are very well separable, and not only are they separable, they're very well distinguishable while separated, so that you can say, here's a set of causes and here's a set of effects. And obviously, complicated physical systems like the universe do not have separable causes and effects. You might be able to witness a cause and effect scenario, but I think it's very naive to assume that you can just say, like, I'm going to take this bundle of things for an event and these are all the causes and there's no other causal information left in that thing. Like, I found all the causes, I'm done. That's not really how systems interact. They're much more complicated. They're much more dynamic. They're impossibly opaque to analysis. And so myself, I am a proponent of the method I'm about to talk about because this philosophical statement speaks to me. I think of the universe as one thing trucking along to some secret differential equation none of us understand. And everything that I could measure about the universe is contained in that attractor I would draw for the universe. It would be in a lot more dimensions than that. I would need somewhere to the order of as many dimensions as I have independent particles in my differential equation, which for the universe is a lot, but I can imagine that large attractor, and I can imagine that anything I would want to measure, like the position of my pen in space, is somewhere one of the little sub-dimensions, one of these little projections that I can imagine looking at of the whole attractor. And so I'm going to show you what these attractors look like for the actual set of solutions to one of the chaotic regions of the Lorentz system that we have over on the left. This is a very popular picture. If you've seen causality stuff before, you've probably seen this picture somewhere. This is the set of solutions, attractor. Ooh, actually, I just want to look at the blue one. We'll come back to the other ones right now. This M thing is if I found a solution, x of t, y of t, z of t, and then plotted an xyz, a three-dimensional plot of that curve. And so this object, say, is starting maybe over here on this side, and it's following this line as it goes through. And you can see it like kind of weirdly swaps between these lobes back and forth. This is why the Lorentz attractor is called chaotic, or at least it's chaotic in this regime, because it's doing this weird swapping back and forth. And until you just simulate it and see what happens, you can't really tell exactly what it's going to do. Okay. So now what I want to do is I want to think about a different attractor. I want to think about a different state space I could draw, because let's say that let's say I don't get to know anything about that one, or maybe I do, maybe I don't. Let's try and build a different one. I will say you can't measure this thing. You can measure quantities that would let you plot it, say, but in general, it's not simple to measure all of the different position and velocity states that your system could be in. To do this, you would sort of inevitably have to measure your system for an infinite amount of time to make sure it populates all of the little points that are available in the system. Since you don't have an infinite amount of time, you got to do something better. So instead, let's think about taking my x versus t and trying to turn it into maybe a different kind of state space. If I can maybe try and form a state space just from x versus t. One x versus t. Not a lot of them, right? This plot I drew above, this funny shape in state space, occurred because I allowed the system, or I measured enough things in the system to be able to populate all of the different states that go inside of that attractor. So I witnessed every possible combination of position and velocity that that thing could have. Obviously, it takes a long time to do that, usually an infinite amount of time, so we don't want to do that. And instead, what I would like to do is to try and form an attractor from a single time series data. One time series, one function x of t. If that sounds impossible to you, well, it should be, but it's not. So what we're going to do is we're going to form a set of things. And this set is going to look very terse, but bear with me. We're going to turn this into a set of vectors. And those vectors are x at t. What do I want? I want x at t naught, x at t naught minus tau, x at t naught minus 2 tau, etc. My curly brace scroll down. My curly brace notation, in fact, what I'm going to do is I'm going to scroll, I'm going to grab you. What? Thank you. Maybe a little farther. Okay. I just want to introduce, I want to be clear about this curly brace notation. What this means is find me a t naught inside of this functional range over here, inside x of t. Okay, say it's 5 seconds. I'm going to form one component of a vector based off of the value of x at 5 seconds. And then let's say my tau here is 1 second, so it's a 1 second delay. I'm going to form the second component of a new vector by the value of x at 5 minus 1 seconds. And then my third component will be x at 5 minus 3 seconds, or 5 minus 2 seconds, and then 5 minus 3 seconds, 4 seconds, etc. until, well, I mean, obviously there's a limit on how soon I can make these by the number of components that I want, right? But then I'm going to do this. I'm going to build up a set of these things for every, I don't have my pen anymore, for every t naught. And then I'm going to have a big set of vectors. I'm going to have as many as I can. You know, if my time series is capital T long, this means I have, there's approximately, what, t minus, how many components do I want? What do I even, I guess I'll say there's, I'm going to do something really gross. There's an epsilon number of terms. There's a reason I'm doing that. So there's about t minus epsilon number of vectors in this set. I know this is looking pretty gross. Bear with me. It'll get worse. So this is what we call a lag vector, and this is a set of lag vectors. So this thing up here defines what is a lag vector. And this is the set of all lag vectors I can create out of my one time series. So notice what we did. We took one time series data that you can just measure. You can just watch the spring move as a function of time. And from that one time series data, I have determined hundreds, possibly, of vectors that describe this data. Okay? Now, what I want to think about doing is give me a big old space. Might need to be a lot of dimensions for the sake of argument. Let's say it's 2-dimensional. I know I didn't draw 2-dimensional vectors up here, but let's think about the space of x at t naught versus x of t naught minus tau. Notice what we're doing here. If this point is plotted on this space, that means there's a time at which x right now was at x naught, and tau ago was at x1. This is a state. And if I did this for as many as I needed to, I can actually describe the entirety of this data set with like with this set of lag vectors. I can describe every possible thing that I could do with this data set with all of these lag vectors. This represents a state of the system, which might make you wonder if there's a connection between this figure I just drew down here, where, you know, if I keep finding these points, I keep populating this with points, I keep watching my system do things, maybe what I find is I find something that looks like this. And inside of this thing is a bunch of solutions, is all the information about the system boiled down into this set of points that occupies the volume in this funny vector space that I drew. Yes, there is a very smooth relationship between this thing up here and this new lag space thing down here. This has a very special name in the literature. This is called, and this is a really cool name, this is called a shadow manifold, which is just the coolest damn name for anything in math, and it's way less interesting than its name implies it is. But there's a really important result here, and it's got a name, and the person's name is attached to it because it's so important. It's called Taken's theorem, and it says that if I have the shadow manifold, which I will call M with a hat on it, I don't remember my math terms. Oh no. There's a mapping between M and my state space, which I will call S, I guess, because I've never given state space a name before, and it's S now. There's a correspondence between M and S. That correspondence, in very, very mathematical terms, if you're one of those people, is diffeomorphism. So it's an isomorphism, but for manifolds, which says that they are not the same. They are not the same shape, but every point on one can be mapped to a point on the other, which means from a structural geometry perspective, they are identical objects. What that means is we can, instead of going to this thing up here, which is like arcane, this is a bizarre thing to construct, and it requires you to witness your system for so long, right? I have to sit there and just let my system go and watch it and wait for it to populate all the different states that it could be in. But instead, what I could do is I could form this lag space. I could form this lag space out of only one of the coordinates. I could form the shadow manifold, is what I should be calling it, out of the observation of a single coordinate of whatever my big system is. And this fancy math theorem I have here at the bottom says that if I build this thing, if I build the shadow manifold, it is the same object mathematically as the state space that I would find if I just measured the damn thing for a really, really long time and was very delicate about my measurements. Now, you can imagine that I could also do this thing for this Lorentz system that I was talking about earlier, since there were 3 coordinates. I could make a Z shadow manifold, so I might call this MX. I could also make an MY and an MZ. Or I could make an M for each coordinate that I have in my system. For me, as a biophysicist, that means the measurements that I'm looking at are observations about cells, microscope measurements about what cells are doing. I have as many manifolds I can make as there are cells in my system, right? I can make one of these for every single time series data that I take. Here in the Lorentz attractor, in the Lorentz system, it means that I have 3, MY, MX, MY, and MZ, and they look something like this. So here, this figure has shown the overall attractor M, which you think of being a set of functions x of t, y of t, and z of t that satisfy this nasty system of equations. But I could also think about the lag space projections of this thing, where mx is just the x information encapsulated in a single plot, and my is just the y information encapsulated in a single plot. But what I've done is I've built it out of only measurements of y and only measurements of x. This is incredibly powerful. This is nonsense levels of powerful, because it means that I don't need to know the differential equation that a system abides by. I can build these out of just measurement. I can build these out of measurement, and I can build these out of pretty finite amounts of measurement. I don't need a ludicrous amount of data to populate this shadow manifold to the point where I believe that I'm witnessing the truth of that coordinate. Okay. What did I want to talk about now? I think I will talk about what I'm doing. And I probably won't go into too much more today because my brain is dying. So let's talk about some biophysics. This is where I'm going to lose the other half of people who are watching. I have a cell. I have another cell. I have another cell. And I have another cell. Here are 4 cells. In reality, cells don't look like this. They look like a bunch of different things. They'd be much closer in contact with one another, but who cares? For the sake of argument. Actually, I'm going to do this 3-cell case because I think this is more interesting. So, an important feature of human biology, and in fact all living thing biology, is tissues. Tissues are organoids that are formed from combinations of cells working in concert with one another. So those cells, whatever the cells are, they're usually some kind of like muscle thing. They can be, tissues can be formed by all kinds of different cells. They're going to form some kind of collective. They are going to attach to one another in some degree. They're going to share information with one another somehow, because tissues on much bigger than cell scales, on like global scales, in terms of the cell biology, can do things that individual cells can't. And the only way that like groups can do things that individuals can't is by organized action. And wow, I just talked about unions. Cool. I managed to get unions out of cell biology. Organized action is the only way you can do anything. There's your other lesson for the day. But this is what a tissue is. A tissue is a group of cells acting in concert to achieve some common goal. And central to our understanding about how tissues function is the role of the cells in that tissue, and even more specifically, what cells are dictating where the bulk should be going. Like, what cells are giving the commands? What cells are the boss? What cells are higher up in the committee of cell movement decisions, right? And so let's say I have a star cell here. This star cell is a smart boy. This star cell knows what's going on. It detects stimulus beautifully. It's got its ears to the ground. It's waiting to see what's happening in the body, and it's ready to tell all the cells around it what to do in the event that something comes around that it needs to react to. Okay? And so I know from biology that if I can detect this cell, I know, like, there's no other way for this to happen. This cell needs to be giving information to its 2 buddies, because it's what we call a leader cell. So this guy's a leader cell is our name for it. Other names for this are pacemakers, which we borrow from heart technology, but I like to call them leader cells. So this leader cell is very perceptive and it's very vocal. There are possibilities that there are other types of cells that are very receptive but not vocal, or cells that are very vocal but not receptive. Those are outside of the model that I'm building right now, so I'm going to ignore their existence. But if you're a biophysicist watching this, like, leave me alone. So there's a problem though. What happens if I measure, let's give these names. So here's cell 1, here's cell 2, and here's cell 3. What happens if I measure cell 2 and 3? Can I say anything about this arrow? Not really. Or I shouldn't, at least, right? Because I see that these, I know a priori, or I can just look at this system and say, okay, the leader cell is giving information to cell 2 and cell 3. But what if I accidentally tested cell 2 and cell 3? How do I know that cell 2 and cell 3 aren't communicating with one another and they're actually getting co-information from cell 1? Let me back up a little bit to the more fundamental question here, is if I have processes A, B, and C, and all I ever do is measure A and B, and I find out that A is causative of B, how do I know that there isn't a secondary effect where C is giving information to both A and B, and it's giving just a little bit more information to A? This is called a triangle motif. This is probably the hardest question in all of causality to deal with. Your causative methods are always going to be, or almost always going to be, insensitive to this system, because there's really no good way to unentangle or to disentangle the information that C has passed on to its causative progeny without like actually knowing that C's there. Like, black box this, right? If I don't know that C exists, how do I know that A is not causing B? I don't. I have no way to tell this. And I can conclude a whole bunch of erroneous things from this relationship. Or I could say, as an example, let's say that I have a system of things. I have water quality and earthquakes. And what I say is, but yeah, the lizard people are causing fracking and earthquakes. Damn, you got to that before that was right where I was going. Dang, Peanut Gallery, you're on top today. Okay, so water quality and earthquakes are two things that I would be interested in investigating for no apparent reason. Let's say that I measure the water quality monotonically decreasing in time, and I measure earthquakes monotonically rising in time. And I might say, in much the same way that someone in years past would look at a rise in consumption of ice cream and a rise in polio cases and conclude that ice cream causes polio, you could very easily conclude from this situation that, or I guess I could flip this plot just so my example is slightly more parsable, which is say that this is lack of water. Yeah, that's right. I flipped it. So this is the bad direction. Okay. Looking at these two plots, I might be able to conclude that maybe earthquakes are causing the water quality to become bad, or maybe the water quality is actually causing earthquakes. And like, I can conclude so much. I can go to conferences and present this data. And as long as there's no one who's in on the system and understands what I'm talking about, no one will catch this. No one will see the problem in here. And if then I tell you, like, BT dubs, I only measured where fracking was, that's a really important thing to say. Because what's actually happening in that causative system is a triangle motif, where fracking is causing earthquakes and fracking is causing the water quality to go down. And so what's actually happening is the water, the earthquakes, and the fracking is that the fracking is causing the earthquakes, and some portion of fracking is causing the water, and some portion of earthquakes are causing the water. And it is much more strongly hypothesized that the fracking is ruining the aquifers, because like, earthquakes aren't known to totally destroy the quality in aquifers. If anything, they're going to drain the quality. They're going to drain the aquifer. They're not going to like make it dirty. So this is again the statement about importance of knowing what the presuppositions of your data is. Since I only did this where fracking was, I've been like, man, damn, all these earthquakes are making the water bad. Man, that sucks. I guess we just got to deal with it because it's earthquakes, and it's not like we can stop earthquakes from happening. And you report back to the Committee of Environmental Policy that you have been invited to in Washington, D.C. It's some like lobbyist-laden affair, and present your data, and everyone goes, sweet, we can keep fracking because clearly earthquakes are causing the problem and we're done. And I have earned my $400,000 check from Fracking Industries. And my job is done. I have successfully misled the scientific community. And I'm not trying to say that every scientist out there who accidentally doesn't include important information and ignores the triangle motif behind their data is I was going to say maleficent. I'm not going to say that they're malevolent. You can do this without even knowing. As example, the system that the method that I'm talking about from this causation and complex ecosystems paper that I linked up at the top, and the process that I'm going to detail probably next stream that I do, probably not today because it's going to take too long, was a method called wait, It's not that one. It's oh god, I have to, sorry, I'm trying to, I know that this is correlation cross map. There we go. I knew the acronym. I had to remember what the actual name was. Correlation cross mapping. You don't need to know what this is, or like, we're going to talk about it next time. So like, I'm not going to go into what this is, but the method that I'm using in my research was created to handle one of these triangle problems. And the triangle problem was, I look at, this was the Scripps Institute of Marine Biology down in San Diego. So they were very concerned with fish populations. And I could be misquoting. I think it was tuna and sardines, but like, don't harass me if it's not tuna and sardines. I think what they were doing is they were looking at sardine populations and tuna populations and witnessing that as the tuna populations were in global decline, the sardine populations were in global increase. And the conclusion of a lot of ecologists, a lot of marine biologists looked at this situation and they said, well, I mean, okay, we could probably build an ecological model in which some part of the sardine proliferation is causing the tuna to have less available food sources. It's causing the water around them to be less clean. It's causing any number of ridiculous, or not ridiculous, they're very scientifically sound conclusions that you could make. Yeah, it could be the sardines are pooping everywhere and causing, you know, all number of different dehabitation problems for the tuna. Further obviously, this is a real big problem for fish people, right? Like, well, not the fish people that live under the sea, but the fish people that depend on fish for their financial stability, right? If you are a fisher person and you run a tuna boat and you see your tuna doing this is a damn problem, right? And you want to know right the hell away why this is happening, because your future as like your way of life is in jeopardy. And like, you know, all ecological problems ultimately boil down to something is disappearing and we need to know why. And so what this CCM method was able to do was able to detangle the triangle problem because of the way it works, which we will get into next time. What they actually found was not that sardines and tuna, not that there's a causative relationship that sardines cause a causal drop in tuna, but that the unknown third thing was the weather, which feels very annoying and sad and defeating, but it's true. What they noticed was actually that the weather patterns were co-conspirating, that the weather was, I think the temperatures were dropping or something in the ocean region that they were or in the regions in which they were following these populations over the course of a year or two. There was some global weather cycle that was making I think the ocean much colder in the region, and the sardines were much easier, had a much easier time repopulating in colder weather than the tuna did. And so it obviously has, you know, I mean, not obvious from an ecological perspective. There could be a connection between what sardines do to their environment and what tuna don't want happening in their environment. But the much more physically sound answer, that has been reconfirmed by many other experiments, is that it was actually a co-occurring triangle that was dictating this relationship. And it's not that sardines and tuna have causal relationships on one another, it's that they were both screwed over by the weather. Well, one of them was, at least. And so the method that I'm going to talk about next week is this correlation cross-mapping method and how it relates. Oh, hello, sir. Welcome to nearly the end of the stream. So I'm not actually flaming you. I'm just like, yeah, no, you're fine. You're fine. Like, for the VOD watchers, tell them what happened. Oh yeah, Austin's a VOD watcher now. Austin showed up late to the VOD. No, it's fine, dude. I'm not harassing you. Yeah. Oh, you know you're fine. Okay, that's a statement. So we've done some stuff. Just to clue you in on what we were doing. You know what? I'm gonna get to my wrap up here in a second because I'm gonna be like not doing this for very much longer today. So ultimately, the reason that I want this method is because when I go back to my cells and I look at systems that do this, where all of these cells are populated next to one another. I want to find what out of this giant bunch of grapes I've drawn are the cells that are leading this environment. Which one of these are the leaders? How do I tell? That is the worst star I have ever drawn in my entire life. Oh my God. You know, which ones of these are the important ones? And how do I detect them? What do they look like? What do their signatures look like? Well, I don't know. None of us know. We don't know unless we go in and actually stain for the formations that they are biophysically making with one another, which is a very intensive process, and that's what labs with money get to do. And like most physicists, I am not in one of those labs, or at least not one that doesn't have money for my shenanigans. So I ultimately want to disentangle this monolayer and figure out what's happening in it. And that's going to require me not only to take data about what these cells are doing, but to disentangle not just a triangle problem, but this has a dimensionality of up to 1,000 to 2,000 cells in it. And every single one of them has some measurement that I'm going to take with respect to time. What I'm going to measure is the intensity with respect to time. And we're going to use the single intensity measurement for each one of these cells and construct the structure of the entire network of the tissue. We are going to inform all of these arrows throughout the whole structure by using this method that I have talked about a little bit down here that was invented for tuna and sardines, so it's totally appropriate. And we're going to see what we get. Now, that's going to be next time. So first, I'm going to go back over what we were doing just to kind of rehearse what we did today. So today has been all about causality and the features of causality, and in particular, how all science is presupposed by some level of intrinsic biases and intrinsic what am I measuring and why am I measuring it that is inseparable from the data you're taking. And causation is very, very dependent on the questions that you're asking, right? If A then B depends very fiercely on what A and B are and what secretly you're presupposing, as if I presuppose C, D, E, F, G, H, I, J, K, then if A then B is a very different statement than if A then B. It's an incredibly different statement, and knowing which one you're looking at, and hint, it's always the first one, really radically changes how you interpret data that's presented to you. So we started off with this question about does fracking cause earthquakes? And if I'm a manipulative scientist, I can absolutely find you a set of data that shows that there's no connection between fracking and earthquakes. No connection at all. Therefore, there's no connection between fracking and the rapidly declining water quality we've seen in aquifers in the Midwest. Those clearly have nothing to do with one another because I showed you that fracking doesn't cause earthquakes, so we're good. And of course, that depends on where I took my data, what kind of data I took, how I plotted it, how I scaled it, what resolution I interpreted it at, what methods I used to analyze the connection, how long of a region I looked, what the underlying principles about the region that I looked in were, et cetera, et cetera, et cetera. All of those things go on and on and on and on and on. And we do really bad jobs as scientists, and sometimes malevolently bad jobs as scientists. This was a fun VOD. Sorry, Austin. We do sometimes malevolent jobs as scientists, not addressing the presuppositions of our arguments correctly. Most of this was posed as just trying to get to CCM, but like I talked a lot about the philosophy of science a little bit because like that's ultimately what's fun, and because science is boring. So what we said is we can take time series data for A and time series data for B, and we can ask the question about the does in the middle of if we do A, does B happen? Yeah. Exactly, Austin. Like ultimately it's all about, like your data shows what it shows, but your data shows what it shows because you made it show that. And I know that sounds like science conjures answers out of nowhere, but like ultimately that's kind of what we do. Is the only reason we investigate. Nobody goes out and does an experiment just to figure out, like, just to do it. You do it because you think you're going to get a result that's going to get you grant funding, right? So all physics, at the very least, is motivated by the pursuit of money. And so what kinds of things you investigate are going to be limited to the kinds of things that you can investigate and make more money from the grant for it than you spend trying to actually research the thing on a preliminary level. And if it's going to take more money in terms of research to show that there is something researchable, then you will get in grant funding back. You will never research that subject. It will never be talked about in academia. And so there's a whole bunch of missing models and missing physics out there that is not financially lucrative. And like, that's just true. That was a very tirade aside for what relevant to what Austin was saying in chat, but like, it is true. So this question of does is very, very hard. This cave dwelling cold cereal eaters. Yep. This question of does is very, very difficult to manage. And we have old methods like correlations that, hey, OneNote, could I like pan over? Yeah. We have methods like correlations that can tell us that if I have things that look similar to one another, like two springs or like two masses connected by a spring, and I shove one and then the other responds at a later time. No, Maggie really likes to warm her cereal up in the microwave, Austin. She pours a cold bowl of milk, some Cheerios in, and then she microwaves it for 3.5 minutes. Yeah, it's delicious. If the deadpan isn't informing you, no, I don't think anybody out there microwaves their cereal. Yeah, no, like, also she doesn't even eat oatmeal, so I'm not sure why she's even, why'd you put the cold there?
Because I was trying.
I see what you're talking about. The sentence there would be, this is why so much theory happens by cave dwellers who eat only cereal. But you said cold cereal instead of only cereal. And that like set off both Austin and I's like, hey, there's some like, guess what? There's physicists around and someone's wrong in the room and they need to die. Like that was the flag that just got set off. It's like, what do you mean cold?
Y'all are assholes.
All cereal's cold. Owned. Like, like, you just said something wrong and now your life is forfeit. Okay.
I know it.
So one method that we have to analyze things that look similar is this correlation idea. And this is just ancient, right? Like this is hundreds of years old. This idea that if two things look similar, I think this was Francis Bacon who first established the idea of correlation and causation. Like this is old as shit. Like this goes back to at least the antiquity of like European science, right? So, but as we discussed, for certain functions, certain regimes that you can imagine looking at, the correlations do not result in physically meaningful results. Because there can be some functions that look very similar at certain times, look very different at other times, and look completely unrelated to one another at other times. Kevin Bacon? You thought I said Kevin Bacon? Kevin Bacon, known scientist and philosopher. Yeah. Yikes. I don't think I've ever been so sufficiently derailed by thinking, like, by trying. There's a Footloose joke in here somewhere, and I know you're hinting at it. It's somewhere in there, and I don't have the mental energy to, like, dig it up. So after we decided that correlations are going to be really bad and that these integrations don't always yield you physically meaningful results depending on what you shove into them, we started talking a little bit about differential equations, and we introduced the Lorentz model for heating and cooling of two-dimensional fluid planes, which gives you some goofy stuff if you actually try and investigate this, particularly in the chaotic regime for special choices of sigma, rho, and beta in that model over there on the left. And then what we said is, if we just take our coordinate x, one of the three coordinates that we're tracking in this differential equation, and we sample it over time by looking at its position and its velocity, and just at t equals 1, it had this position and this velocity. At t equals 2, it had this position and this velocity. And we just keep doing that for literally ever and let the system just continue going. We can envision that there's this shape that will form if I plotted all of these things, where the shape contains all of the solutions for the x coordinate to this differential equation for a particular choice of its parameters. I call this thing a state space because it is a space in which I represent the states of the system, where a state is I have a position and I have a velocity and I'm here, and that's a state. It's what I said as a philosophical statement about causality that is the underpinning of this model that I'm going to discuss next week, which is this CCM model. Is that every observable quantity is a projection. Let me scroll up. Is the projection of some holistic attractor, where there is some state space that is really, really big that I can imagine the solutions to the universe set in, where the solutions to the universe refer to one giant differential equation that represents the universe and the set of solutions to that giant differential equation. And if you understood that, you would know where every object in the universe is going to be at a later time and what its properties will be. And obviously, yeah, I don't know how it ended up looking that nice. It just did. I got lucky. If you knew that giant universal attractor, you would know everything there was to know about the universe from now until the end of time. And that would be pretty cool to know. You would probably die from the eldritch horror of having that much information. But yeah. So what we then decided to do is we said, well, this is a really cumbersome thing to do. To try and wait for all of this, for the system to continue evolving long enough to actually sample the state space sufficiently, you will need to just let it run for a long time. And so what we instead tried to do is we made a secondary space where this thing is a lag space, where instead of plotting positions and velocities, I've plotted positions and positions at a different time. This thing forms what we call a shadow manifold, and the vector and the points in this thing are formed from what we call lag vectors. Did you Google that, or did you write that from memory? It's very important to me which one it was. Okay, because if you wrote it from memory, we were gonna have a problem.
I knew what it was, but I can't spell it.
Sorry, Maggie, in case it's not picked up in the VOD or whatever, Maggie wrote down the Cthulhu death chant, and anyone who has that memorized, Cthulhu Fatagan, yeah, it just very much distracted me, and I was very concerned if she knew it from memory, because that would be weird. Not saying anyone who knows that from memory is weird necessarily, but I have a suspicion about you. So we could think about, for this Lorentz system, drawing the shadow manifold formed from the lag vectors for the x, the y, and the z direction. And what we know from fancy mathematics that I am never, ever going to go into because it's way above my pay grade, I just know it's true, is that the shadow manifold and the state space are smoothly connected to one another. In the language of manifolds, there's a diffeomorphism that relates them. In the language of people who speak actual words, it means that they are the same thing. So the shadow manifold I make and the states, the sufficiently populated shadow manifold that I make is going to be basically identical to the state space I would make if I just kept sampling the system. They're different coordinate spaces, right? I'm plotting positions and positions a while ago versus positions and velocities, but the shapes they make are, they're not identical in the two spaces, but the things they make are identical. There's mathematics here, and it's not important to even talk about. And so if I imagined these x and y projections for this Lorentz attractor M here, this is what it looks like in x, y, and z space. I can form an x projection and a y projection of this M thing by just plotting the x shadow manifold and the y shadow manifold. And so what this is really doing is this is telling me that my coordinates are projections of the global attractor, which is this philosophical statement that we said right here. And so ultimately what I'm going to be doing next week to analyze this system, or to analyze my biological data, is using these ideas of lag attractors and this method that I hinted at called correlation cross-mapping, where we're going to, we're gonna figure out how what the tissues do and how their structure is formed, or ideally we're gonna do that. Of course, my name not being in nature means that this didn't work super well, but we're gonna do it anyway because it's fun. It's not aw, it's good because grad school sucks. Oh yeah, also fracking causes earthquakes. No one should be fracking anymore. Like, dear God. Cool. That's basically it for what I wanted to cover today. I got through the presupposition material for but my fossil fuels. I need to burn things to feel like a human being. I'm not a real man unless I'm burning something. So let's get out there and destroy the environment to get my masculinity back. What? I gotta burn bridges instead? Yeah. Yeah. So this has been a little diatribe about causality. Hopefully there was something cool and interesting in here that taught somebody something. Or Capitol buildings. Wow, that's not topical and or arsony or terroristy. Austin. You might want to send an edible arrangement to the FBI assigned to you. The FBI agent assigned to you because watch that. Yeah. So this has been Brenden for Physics University. We covered some causality stuff today. I know this was very weird from our previous content, but this is much more in line with what physics looks like at a high level. We don't do free body diagrams. We look at models and see how they apply to the universe and what we can learn from them. Was there anything else I had to say here? Please make sure to, if you are a VOD watcher, please make sure to subscribe down below. Then you'll get notified when we post new videos. And please come and hang out in chat if you're available to. Our Austin doesn't do real physics. When did that happen? Real physics isn't free body diagrams. Oh, I did say that. Yeah, you don't do physics. So VOD watchers, please subscribe so you can get notified when new videos come up. Please come and hang out on chat. If you go to our Twitch channel, twitch.tv/physicsuniversity, don't forget the E. Our schedule is posted below our channel, and we're just on doing whatever the hell we feel like at that time. So please stop by, tell your friends that we exist. We want to help you with homework and learning and just like make your physics journey or your journey into becoming a science aware person more entertaining, more engaging, and more accessible. Yeah. It's been real. What do people say here? Bye? Bye? Cut the